Okay, in the last video, we essentially solved this problem here. This integral right here determined to be equal to this right here. And it's kind of a complicated expression, but really deriving it was not difficult. What we had to do, first of all, is just some algebraic manipulations to get this into this form, with our 4 factored out over here. And as soon as that happened, we realized that this was amenable here to this type of trig substitution, where we take our variable, which we're considering x plus 1/2 a single variable, and setting it equal to the tangent of theta. And as soon as we made that step, the rest of it pretty much fell into place. Dx would be the secant squared of theta d theta. This denominator would be 1 plus the tangent squared of theta, which is the secant squared of theta with a new substitution here. And then from this, it's a simple matter to find out that 2x plus 3 is this. So we had this became this, this became this, this became this. And eventually it came down to these two trig integrals that we could readily solve. The integral of the tangent of theta, we had to remember, is minus the natural log of the cosine of theta. And of course, the integral of d theta, that's just theta. So we readily solved our trig integral. Then we had to go back and convert things into our original variable x to get the proper expression for this integral here. So the tangent of theta is this. So theta, that would just be the inverse tangent of that. That's no problem. But we also have to know what is the cosine of theta. And that's when we go and we draw the triangle. If this is theta, the tangent of theta is the side opposite divided by the side adjacent, and then this is the square root of this plus this, which equals this expression here, x squared plus x plus 5/4. So finally then, we could substitute the cosine of theta from this triangle. We got this, and from theta, we already had that figured out. So minus 1/2 the natural log of 1 over the square root plus 1/2 the inverse tangent of theta, x plus 1/2, plus an arbitrary constant of integration should be the solution to this integral right here. And we asked you to come back just because, not because this is wrong, and I think in any circumstances would be considered a correct answer, but maybe we thought we might be able to manipulate this a little bit more. And here's why. This right here we can write as minus 1/2 the natural log of x squared plus x plus 5/4 to the minus 1/2, since the square root is in the denominator. Here we're working with this expression here, minus 1/2 the natural log. This square root is in the denominator, so we could write it as this quantity to the minus 1/2. And because these are logarithms, we could rewrite this as 1/4 of this logarithm. And now what we're thinking of is, let's write it like this. 4x squared plus 4x plus 5, everything divided by 4. Dividing by 4, we would get this expression here. So, going in this direction, it would be this plus 1, but multiplying it by 1, 1 being 4 over 4. So this is now this, And again, because of logarithms, we can rewrite this expression. This would be 1/4 the natural log of this 4x squared plus 4x plus 5 minus 1/4 times the natural log of 4. Oops. Let's see. We had this here, which we could rewrite as this here because the square root is in the denominator, so it would be to the minus 1/2. Then because of the property of logarithms, we could write this as 1/4 of this logarithm. And again, because of the property of logarithms, we could write it as the log of this minus the log of the denominator. So we rewrote this like this. And this is just a constant, which we could lump together with this constant. So finally then we could say, well, the answer to this integral way up here would equal 1/4 the natural log of 4x squared plus 4x plus 5 plus this plus 1/2 inverse tangent of x plus 1/2 plus lump this and this as a different arbitrary constant. So our attempt was to take this expression here and simplify it a little bit based upon the properties of logarithms and the fact that you have this constant here together with an arbitrary constant of integration. So we could take this, which is a perfectly acceptable answer, but we could do a few little manipulations with it and get into a slightly cleaner form. Okay, that's it for this problem. Come back and join us for some more videos, and we'll see if we can solve some more problems.